We can start now. Okay.
It's not blank, but it's okay, right? Hello, everyone. Hope you can hear me well. Welcome back. We resume today with our series of the workshops that are having advanced topics. So we are done with the basic programming and mathematical foundations necessary for data scientists, and we're continuing with a series of more advanced workshops. Just welcome again. Good morning, good afternoon, or good evening, depending where you're located. If you're with us for some time already, welcome back. If you're new, welcome to the second Data Science Summer School organized by the Hertie School Data Science Lab. And this year we are organized and funded by Hertie School, which we're really grateful for their support. As I mentioned before, the school kind of is split on the introductory workshops that we're done with, but you can find all the materials of these workshops on our webpage. And now we're continuing with advanced workshops. I'm gonna tell you a couple things about organizational and technical details. Sorry for repetition if you're with us for some time already, but for those who are new, just to repeat that if you are on Zoom, you probably are muted and your cameras are off upon entry. Please do not unmute yourself or turn your videos on unless you do have a question. If you want to ask a question, you can put it in the chat. We will answer the question in the chat or address it to the instructor. Or if you do want to speak up and actually ask the question out loud, you can raise your hand, or judging by the amount of people here, actually it's not a lot of us today, so probably you can just unmute yourself and just ask a question. And actually Marcel said that it's okay with him if you just like jump in and ask the question, so it's totally fine. If you are in the parallel stream session on YouTube with us, you could put your questions in the comments box, and we will try to answer the question there or address your question to the instructor. Also, just a quick note, we do still have a room on Zoom, so if you do want to jump on Zoom and not stay on YouTube, please, you're more than welcome to do that. I also want to remind everyone that the Zoom session is being recorded, so if you do unmute yourself and turn your videos on, you're automatically agreeing to your voice and your image being recorded. Thanks in advance for following these rules, and I just want to keep on with introducing our today's workshop. We're continuing with the as I said, the first workshop in the advanced series, and today we have the workshop on generative adversarial networks, GANs, and we have Marcel Neuhofer as our instructor today. Marcel is a PhD candidate and research associate at the Chair of Political Science, Quantitative Methods in the Social Sciences at the University of Mannheim, and research associate at the Chair of Statistics and Data Science for Social Sciences and Humanities at LMU Munich. His research focuses on quantitative methodology, where he's specifically interested in the application of deep learning algorithms to social science problems. And he's also co-founder and contributor and the visualizationalist of zweitstimmte.org. And without further ado, I just want to give the words and then the place to Marcel. Marcel, the floor is yours. You can share your screen now and have fun, and welcome everyone. Good luck.
Thank you, Olga, and thank you for organizing this awesome summer school. And it's like a great honor and also pleasure to be back after instructing a course in machine learning last year, and this year one of the advanced topics on generative adversarial nets. And also I'm excited that so many participants are here in Zoom. And I hope like in the first like 10, 15 minutes to get to know you and your interests and what you want to get out of this course a bit, like even though it's so many. And then we will dive in right into the like class for today. I hope you can all see my screen right now. And before we get started, some housekeeping. I guess you also found like those links in the chat already. Like if you want to follow along the presentation in your own pace or go back a few slides, you find that at the first link. Or like look at the presentation after the like course today. And we will have 3 collab workbooks that we will walk through and work through along the way that you will find in that GitHub repo down here. And also they will be up like after the course if you want to redo it or do it on a on your own computer. All right. Yeah, like I guess Olga already said like everything like that can be said about me. So just a little context about generative adversarial nets. That's actually a method and a technique that I used in my own research. So like there is 2 main directions there. Like one is generating synthetic data for use in like privacy protection so that you can share data freely with others. And the other big application there is multiple imputation. So like it's, yeah, it was a great fit. I was very happy like to be asked to provide this course at the summer school. And as Olga also said, and please do that, interrupt me at any time, like if you have a question, if it's going too fast, too slow, if something wasn't clear, let me know, and I will answer your questions or try to answer them and like accommodate any other issues. All right, so let's get started with like learning a little bit about you and your interest in participating today. I set up a little Menti. So if you follow that QR code, you will get to an entry mask of where you can put in like 5 words or 5 phrases. And the question, or like it's an open question, is why are you interested in generative adversarial nets? And there's no right answers, there's no wrong answers. I'm really honestly just curious about like what brought you to this class today, and like maybe even like what your goals are in your own research as data scientists, social scientists, with generative adversarial nets. So if you follow that QR code, just type in some words. It's all anonymous, and it will generate a nice word cloud that we can look at together to learn about your interests today. And then I hope like that this matches with what I have in mind for this class. If you have the slides open, like there is also the link in there, so that therefore I can like here you can also just copy that link. For some reason, the access code doesn't work, and we already have some first interest. We have machine learning knowledge, deepen knowledge, data-driven analysis, job. That's interesting. Job preparation, I don't know them. That's a very valid interest in learning something. Reorientation. I guess the yellow ones, they probably come from one person. Prior experience from science. Let's just reload it once more to see if more. Curiosity. That's always great for science and research. Diversify skill set. PyTorch. We will work with Torch today, so that's a good match. Although it will be from R, but that was very, very similar to what's going on in PyTorch. And while those come in, it reminds me a bit like of how I also got started with like generative adversarial nets a couple of years ago. Like curiosity in the center here was really what started it. And like a bit of hype about it as well, like because of all the cool or fancy applications to images, and then trying to think about like how this could be useful as a political scientist or like / data scientist. So I hope like to take you on that journey a bit, to show you why I think it's very relevant to understand the basics, and then also get to like fancier applications where we look at images and also privacy preserving synthetic data. All right, let's just reload once more that like everyone who wanted to submit something can see it here. Yeah, it's like it's a nice, colorful basket of different interests, and I guess we can try to work around those. All right, so I guess if you heard the term, like even if it was just for the purpose of this course, and you maybe Googled it, what you probably came across is like pages like "this cat does not exist." It's also linked up here. That generates you nice pictures of cats that don't actually exist. So all those cats are actually generated by generative adversarial network that learned to generate fake cats. And they look pretty real. Sometimes you will get, yeah, like this one, like if you have a cat, you will probably see that like the eyes look a bit weird. But overall, they look pretty impressive. And that's, I guess, a fun application, right? Like, who doesn't like to have a machine that can generate like more images of a cat? However, like the same also works, of course, with persons, right? And those are really, really impressive from like what is called the style GAN implementation by people at NVIDIA. So they have lots of compute, lots of time, and probably also lots of training data. And they have very like high definition images of persons. And again, this is like a page, this person does not exist.com. It's linked up here. If you want to generate like fake persons by yourself as well. Let's just look at another person here. And also, like if you do it like long enough, you will see sometimes weird artifacts that give away the fake person, but most of them are pretty good. And like what's also awesome about this page, this person does not exist. It's a great resource to learn about GANs as well. So you get links to all those like implementations that they actually use. And also like they generate other stuff than cats and persons as well, if you want to see like horses or chemicals. So this is what drew me into GANs at first, like this amazing capability of generating fake data, right? And images in particular, very hard, or seem to be very hard to generate by machines pre-GANs. And honestly, it doesn't stop there. Like there is also GANs for video and text to speech, where like you can basically have voices say anything you want that those voices never said, like in real life. And that's pretty awesome, like as like this company Descript offers this as like a tool to edit video or podcasts. So it basically transcribes what you say into a microphone and when you record it, and then gives it as a text. And then you could edit the text, and this would in turn end up to be like edits in the actual voice recording or in the actual video recording in your own voice. Or like this overdub where you can try a demo on their website is like if you need like a professional sounding voice to talk over like maybe a video, and so you could enter arbitrary text and it will produce very, very impressive results. So this is all nice and shiny, and now I will put my social scientist hat on for a little bit. Why I think we should care as social scientists, as data scientists, who also think about ethics in research or in our applications. And because we care, I think we should also know what's behind this, like from the ground up, and build an understanding of how those like wonder machines work from scratch. So unfortunately, like that image is not here. Okay, that's weird. But like for example, of course, like you saw those nice pictures of people. You could start to create fake personas, right? Like you can have a picture, but no one real, so no one can sue you. And in the 2020 campaign in the US, like a lot of the rumors and let's call it fake news around Hunter Biden was actually put out on Twitter by a fake persona that had like a GAN generated profile picture. And this was a big story, like pre-elections at NBC, like a big TV station in the US, where they tried to reconstruct like who's behind that fake persona. So I guess that's like showing like that there's always like two sides to a coin, right? Like you can generate nice, shiny images of persons that don't exist. And that's really cool at first sight. But like at the same time, this technology can be used to mislead people, right? So people on Twitter think they interact with someone real that they have never seen. And in fact, it's just an image that is like generated by such a generative adversarial net. And it gets even worse, like if it's not just images, but if it's videos and audio-visual content. And this is an example from actually almost 5 years ago. And it's still pretty impressive, where like this company Lyrebird that still exists created a deep fake of Barack Obama saying like the words that the programmers at this company wanted to say him. And they make it very clear that this is a fake, and like also the message is such that it like is like warning for this technology. And you could easily see how such deepfake videos could be used to influence opinions, to like make people say something they never said, which in turn could lead to real life like outcomes, good or bad. And like if you go and look at this YouTube video, it's pretty amazing, like what the technology could achieve 5 years ago, and like knowing those innovation cycles and like timelines in computer science and computer vision in particular. It's not too hard to see like how much scarier or how much better deepfakes became in the meantime. So like, yeah, it makes it harder for us to trust audiovisual sources. And there's also like a lot of research going on actually to make sure that GAN generated content could be identified, like trying to figure out how this could be identified. Like think of it like as previously, like there was a lot of research and basically data or image detectives trying to figure out if a image got tampered with, and they tried to develop techniques to like basically reverse engineer to figure out like whether a GAN was used. And to be able to do that, if that's your goal, like if you don't want to be on the faker side, but like on the detective side and identifying like GAN generated content, I think it is also necessary or like a very, very good idea to actually learn how GANs work. Oh, by the way, I probably never introduced like this like acronym. So generative adversarial nets or generative adversarial networks are typically just abbreviated with GAN, and like it's called GAN. Like if you hear it. So that's like the bad or maybe also like interesting examples, and this is why I stayed. Generative adversarial nets can also be a very useful method for data sciences. So some examples of applications that have actually been published is, for example, the imputation of missing values. Like if you have like the system of neural networks that can draw new observations, new values from like some underlying distribution, it makes sense to like think about how this could be used to impute missing values. So if you have like a data collection and some values in your spreadsheet or in your data set in your database are missing, you typically don't want to throw away like the whole case because you still have useful information in there. And this, of course, would bias results. And you want to use like a good way of like figuring out what the values could have been like if they were observed. And GANs turn out to be very useful for that. Then another very cool idea is like that you could use those generative adversarial nets to make a copy of some original data set. Like if you have a survey that you collect and you want to upload it to a replication archive, or you want to share it with a business partner. But like privacy laws prevent you to actually share the original data. You could come up with a GAN that creates a copy of that original data that is very close in like the statistical like properties of that copy should be very similar to the, or like in the best case, should be very similar to the original data. And then you could pass on like this synthetic copy. And if you build in some formal privacy guarantees, like your like the problem of sharing the data could be solved, and you can actually share it freely without harming anyone in the data collection and without going against any privacy laws that you might have to comply with. And more in the original line of the like what GANs were first used with, like image data. There is some research out there where they use GANs to generate faces, like visual features of persons, and use those faces or those personas in vignette studies, like in survey experiments. So like they want to, for example, if you wanted to figure out like if some trait like helps to get to be voted for in some country, or if some other traits are discriminated against, and it's very hard to actually use real people for that, especially if those people maybe don't even know that they are part of such a survey experiment. So coming up with like generated images that then like allow you to tune it to the way like that you need it for the survey experiment, and then using them as a stimuli in an experiment is also a very cool idea for like the use in data science or social science. All right, so that's like the short hype intro. Well, I hope like it's generating a bit hype. And now I will give you an overview what we will learn until 2 p.m. today. And we will start with like the very basics of GANs, first on slides, and then we will code a simple GAN using those basics from scratch in Torch in R. And when we go through that, we will see that at different stages of like writing or coding up that GAN, we have to make different choices. And there is like many different design choices that you can make along the way. And so in the second half of the course, so that probably starts around after the break, we will learn about like those different design choices in depth, so that you understand where the current research frontier is. Like I have lots of recent references in there, like if you want to catch up on what GAN research is doing at the moment, and also think about and talk about like how those different design choices can be implemented. And then one example of like making different design choices is then, instead of like our simple GAN where we will really just use simple tabular data, how we can adapt like a GAN to generate fake images and actually implement that as well. But I hope no one expects to see like high definition like faces as we've seen in the intro, because like the time we have to train today is just not sufficient to do that. But we will see faces, like we will learn faces, but just not as HD as the ones in the intro here. And then if time permits it, and I hope we get there, I have like a section on my work with GANs and how this could be used to generate privacy protective synthetic data. Like in doing this, there's like two interesting concepts that could also be useful beyond that application. And one is how to train with formal privacy guarantees like neural nets, and in this special case, generative adversarial nets, and then also how to post-process the output of a GAN. Like we will see that training GANs can be hard, or it's definitely harder than training most machine learning models that you might have seen before. All right, are there any questions at this point? Like I just see like the number in the chat running up, but I'm not sure if it's like anything that I should address here. If that's not the case, we can jump right in and get started with the basics of GANs. All right, so this is a lot of text, and I try to, I won't read the text to you, but I try to use the illustrative example that Goodfellow et al. So that is Ian Goodfellow. He was then, like in 2014, a PhD student in computer science, and he came up like with those generative adversarial nets, like within a research group, and so basically the game, and that's where the adversarial in generative adversarial nets comes from, is between two different neural networks, where you can think of one of those networks as like money counterfeiters, like a group of bandits who want to fake money, like let's say euros, and a discriminator, like a second neural network that you can think of as like the police, or like a financial investigation unit that wants to like get 100% of fake money off the market. Basically, they want to detect fake money and punish the bandits if they like get caught with fake money. And those two groups, they basically don't ever really interact. So basically the group of bandits comes up with like a first guess of what, and that they don't see actual money, comes up with a first guess what like money or like a 10-euro bill could look like, and try to pay with that, or try to pass it basically by the police. And the police get to see like the fake money that those bandits generated. and of course real money, and they can compare those two, and then basically give a feedback to the bandits in the form of like if they if the money was it was easy to see for the police to see that this is not real money, then they will lock them up, so they will punish them. And if the money is good enough to pass as real money, then the bandits will also know, right? Because then they could pay for goods using that fake. And so those two players, like the bandits and the police, they play this for like multiple iterations. So bandits come up with fake money, try to pay something, and get then like the feedback from the police, who compares the real and the fake money. And based on that feedback, they try to improve and get better. But at the same time, the police also tries to get better, right? Like they see more and more real money, they see more and more fake money, so they can also learn better like what's real and what's fake. And this is like a like a game. Like if some of you had game theory, like this sounds a lot like those games in game theory. And it turns out actually that this game has a Nash equilibrium, like an equilibrium where this game basically finds a stable state. And that's the case when, as soon as the bandits generate money that like the police can't distinguish from real money anymore. Like if the police is like maximum uncertain about like if it sees like real or fake money, then this game will enter a stable state where like both groups won't learn anything anymore, right? Because like basically the police is just random guessing what's fake and what's real, and because that's just a random guess as a feedback, the bandits also can't learn anything anymore. And if we reach such an equilibrium, that basically means that the bandits sample like their fake money, like they produce fake money from the universe of real money, right? So they sample fake data from the true underlying data distribution, and therefore it is impossible for the police to know. Unfortunately, like this nice theoretical insight that like in this equilibrium, like the generator, the group of bandits will actually learn to sample from the true underlying distribution, has the downside that to actually prove that such an equilibrium exists, we need both the discriminator and generator to have like infinite capacity. So they must be infinitely powerful, which is of course not possible in real life. However, in that paper, Goodfellow et al. Show that like neural networks can be powerful enough to get to maybe like a local equilibrium or like somewhere close to an equilibrium to actually generate like images or fake money that looks like to human eyes very, very good and appealing. And this is really cool. And like one of the major insights or one of the major breakthroughs in this formulation of the problem is like that before with generative models, computer scientists and statisticians tried to directly model like this, like some generative model. And this turns out to be really, really hard, right? Like to come up with a generative model that produces data that is indistinguishable from like your real data is really hard. And like what they did basically, by introducing this discriminator, the police, they turned like this learning task of a generative model that is hard into like a supervised learning problem, right? The discriminator gets to see real data, gets to see fake data. So you have labels, you have like, let's say the images or like the data as features, and then you can try to distinguish, try to discriminate between like real and fake. And this is surprisingly easy, and setting them up in this adversarial manner actually produces a system that makes use of like discriminative learning using the discriminator to update a generative model. So this is a very, very powerful idea. And for that reason, like is cited very heavily, and there's so many different GANs out there. And at the same time, it's surprisingly simple, right? Like if you look at this formulation of the game between the police and the bandits in like math terms, you have two terms in here. The first is basically the expectation of discriminator scores over real data and the log of that. So the discriminator puts out like a probability between 0 and 1, whether that example is real. And then you log that and take the expectation over all the examples that you see. And like the same thing basically for fake samples. So fake samples are generated by putting random noise C through a generator, and then just applying the discriminator to that and using 1 minus the probability here and log that. So basically this, like it's called a value function here, but in classical machine learning models, this would be like similar to the loss function. It's very closely related to binary cross entropy loss or logistic regression. So you might have seen like something like this before. And now, as we have like those two networks that we want to learn, like one tries to minimize this function, the generator, tries to update its weight such that like the value of like this function is minimized. And at the same time, the discriminator tries to maximize this function. And this is how like this adversarial game can be started in like math terms. And since they are playing against each other, we can also not reach like a minimum or a maximum, right? Like we can only try to find like this stable equilibrium state. So to look at it in a bit more visual terms, what you can see here is basically the two networks that we need, like the generator here and the discriminator here, and like all the inputs to those two networks. So the generator only really gets random noise as input, and you will see in our coding exercise like that it is really just random noise. And I'm always fascinated at like this network learns to produce something useful out of this random noise that is parsed like to this generator neural network. So here this visualization is probably some sort of like convolutional architecture, but like we will talk about architectures later, which makes sense in this example because like this is using MNIST handwritten digits, like as an example here, and tries to produce like a fake number in this case. Then the discriminator gets to see like real numbers from the training set, and fake numbers that are generated from the generator, and tells whether like this is real or fake. And then with this feedback, the discriminator is updated, and with this feedback, also the generator is updated. And playing this for long enough will get you to a point where you will actually start to see something that looks like numbers.
Marcel, there is a question in the chat.
Yes.
What a random noise for this case, especially the type of noise, some characters. So like the person wants to know what exactly random noise is here. Yeah,
that's a great question, and we will also talk about it in depth in like the second section, because it depends on the application, but typically it will be just a let's say n-dimensional vector of independent draws from a normal standard normal distribution. That's what we will use in the first example as well. So we will have a vector of the dimension that we think, and this will also be like at assigned choice, is sufficient to like cover basically the feature space of the fake data that we want to generate. And each entry is just independently drawn from standard normal often. For those image type problems, sometimes like drawing from a uniform distribution between -1 and 1 is preferred, because like you can bound the input space, because you know that the output space is also not like unbounded. And then there is some very recent research about like how to come up with smarter noise distributions. Because it turns out that not every point in this latent space, so basically we set up a latent space that maps to real images or fake images that look like real. And not every point in that latent space is equally likely to produce a good looking image. And there is some heuristics about like how to figure out like what points in that space actually make sense to sample images from. So that's a great question, and like it's a very active area of research. So there is no definitive answer from me at this point, but we will use like a vector, the sample from a standard normal in our example. Are there any other questions? If that's not the case, we can directly jump in and try to code, or like we will code, a simple generative adversarial network from scratch. So from scratch, meaning like we do all the steps that we can see here in this picture by hand, like there's no wrapper function around it yet. And like, I hope, or like at least for me, that's how I typically learn a lot by actually going through code and like thinking about how those abstract concepts translate into code. So to do that, you can follow along here now, or you can also spin up like the Colab workbook from the GitHub repo, and just beware that like this first code chunk, loading or installing and loading the libraries, takes about like 6 minutes. So like if you want to run this, like this will take some time, and it doesn't get stuck. And unfortunately, like Colab is not providing real-time output, at least not very helpful. So at first I thought, oh, maybe it doesn't reinstall what it should do, but it works. And
Marcel,
I
can
preloaded.
you, sorry for interrupting. The font
No.
seems to be a bit too small for people. So if there is
Yes.
a way to like zoom in, that would be great. Thank you.
There is always a way. Is this better?
I hope so. I mean, for me, it is definitely better. Yeah.
That's good. So like I preloaded those packages just before starting the session today. So this like runs immediately, but like if you run it for the first time or whenever you connect to a new runtime, this takes around 6 minutes for me. Like, and I assume like that the Colab runtimes are very similar, so should be around 6 minutes for you as well. So don't worry about that. Like all the code is here, and I hope it's like with good comments so that you can follow along right now and also follow along when you want to work through it like after the session. So in this first code chunk, we will just generate some simple toy data. And I'm using R here, but you could certainly do a very similar thing using NumPy in Python. So we just set a seed so that everyone gets the same toy data. We set a number of observations to be 1,000. And I will show you what this toy data looks like in a moment. Generate like a first variable X that is just drawn from a standard normal distribution, and a second variable Y that is a transformation of X plus some random noise. And it is taking the squares of our X's and adding basically a draw from a normal distribution with like smaller standard deviation, so that we get a bit like noisy data. So it's not a perfect mapping from X to Y, but like a noisy mapping. Then we just put this together like in a matrix in R. Like the first column will be X, the second column will be Y. And that's our toy data that we will work with and that we will try to synthesize. Like we want to generate like a synthetic copy from that toy data. And later on, to actually work with it in Torch, and if you have worked with neural nets before, you probably know this from PyTorch or also from TensorFlow. We need to transform like this object to a torch tensor here. So like a type of object that the torch library can work with. So like that's just transforming like like just changing the type of the toy data such that like torch can work with it. Then we have a quick overview skim of the toy data using the skimr package, which is a very nice library to get quick overviews of data and a simple scatter plot. And this will probably show the best like what kind of data we are working with here. And of course, like if you want to like work with this and play with this a bit, like you could come up with like any other sort of toy data generating process for your toy data to see how this affects like your GAN training later on, and like how it maybe interacts with design choices that we will talk about later today. So the data summary with skimr tells us, okay, this object is named toy data. That's the name I came up with. It had 1,000 rows. That's the number of observations we set. and has 2 columns. And both of those columns are numeric, which makes sense since it's like a draw from a standard normal distribution and like a transformation of that. Then we see like some statistics, like the number of missing data, which we have none here, the mean, standard deviation, and some percentiles of our data. And the same thing for Y. So for X, nothing surprising here. Like that's what a standard normal should look like, a mean around 0 and standard deviation 1. And for Y, we have like this skewed looking data, which makes sense since our transformation is squaring like the X and adding some random noise. That means that like very negative values, so like a -3 on X gets like something larger than -3, I said, like something positive when squaring it, larger than 9. And then we add like smaller random noise. So what does this data set look like, and why did I choose this particular form? It looks like a parabola, right? Like if we didn't add any noise, it would just be like a perfect mapping from X to X squared. And now we have some random noise that we added here so that we actually get something that looks more like real data that we typically work with, right? Like there's always noise somewhere. And why did I choose this kind of function? Because it's not like from a statistics point of view, it's not like without knowing like the data generating process, it's not really straightforward how to come up with a generative model for this distribution. So what do I mean by a generative model? We want to produce a model that samples new points that follow the same relationship. And it's definitely nonlinear, right? And also has like if we would try to view that from the perspective of Y, the issue of like one point in Y maps to multiple points in X, right? Like if we go down here, like probably like if you know the true function, a 6 in or like let's make it 4 in Y could map to -2 or to 2. So it's not like that. It's easy, right? It's 2-dimensional only, and we know perfectly what the relationship is. But it's not too simple, right? Like that we have an immediate idea of like how we could learn a generative model for that. And now we will try to come up with a GAN and train the GAN such that we can actually draw new values from an approximation to this underlying true function. All right, as we have seen before, like a neural network, a GAN is like a game between multiple neural networks, or like in the cases that we look at, between 2 neural networks. The first is the generator that gets random noise as input and produces fake samples as output. And the second is a discriminator that gets the real data and fake samples as input and tries to classify which examples are real and which are fake. And as I said, here we want to generate those fake samples from our toy data. And so we want to learn this distribution and sample fake data. So our goal in the end is to have this generative model. And of course, before we can observe this adversarial game, we need to set up those neural networks. And to do that here, I will use the torch library in R. And like if you're used to PyTorch, the syntax is very similar to what you see in Python. So we first set up like basically a class that is fairly general, so that we could easily use it with like different like parameterizations of the neural network. And there's two important things for the generator network that we need to take care of. And the first thing is like, or that's true for any neural net, and in particular with GANs, it's very important to think about it. Like, what is the dimension of the input? And the input to the generator is our random noise. And what is the dimension of the output? And this is probably a bit different to neural nets that, like, if you ever used or if you ever coded a neural net for prediction, the output dimension is typically like 1, or maybe if you have like a multi-class problem, the number of classes. But here it will be the exact same dimension as our original data set. Then we can also customize the number of hidden layers and the number of units per layer in this particular like class. And we could also add, and we will experiment with that later today, the dropout to the hidden layers. So dropout is like a way of getting additional random noise into the network, which typically helps to converge a bit quicker, and also has a nice side effect that we will look at later. Then it's just set up as a sequential neural network module, where this now keeps track of like how many input and output units we need, and then just stacks like a linear layer with the right numbers, and with a ReLU activation and potentially a dropout layer, or it will add the dropout layer no matter what. But like if our dropout rate is 0, this will just pass through like the previous activation, and then return as like this whole neural network module, where the output layer for the generator is just a linear layer, so like a fully connected linear layer, where now the output has to match our data dimension. So this is important so that we can actually pass fake and real data of the same dimensions to the discriminator.
Marcel, can you, there is a question about the hidden layer. Valeria is asking like about the necessity of a hidden layer. What is it needed for? So maybe you can elaborate about that. Thank you.
Yeah, right. So in like neural networks, how you get like this flexibility of learning nonlinear functions basically is that you stack. So basically, you have two options. So you can go very wide, like research has shown that a network with one hidden layer, and we always need one hidden layer, and like the hidden just means like you have an input layer that basically takes the input as is and passes it to neurons. Then we have a hidden layer that is basically taking care of all the nonlinearities that we might need and care about, and an output layer. And the hidden layer is named hidden because we typically don't care about the input and output of that, right? We care about the input at the data level that goes into our network, and we care about the output. And therefore, like this name hidden layer became a convention. And like a neural network with like one hidden layer and like enough width so enough number of neurons, can approximate arbitrary functions already. However, empirically, like, it's very hard to get enough width. It has been shown that like adding multiple hidden layers, so going deeper, and that's where the deep and deep neural networks comes from, stacking multiple hidden layers on top of each other helps to get those nonlinearities with less width. So there's basically a trade-off between width and depth. And especially for image recognition and then also image generation later today, like the standard are like deep, so multiple hidden layers, convolutional neural nets. But if you want to know more about that, I guess there is a great course from last year of this summer school that should probably still be on YouTube. That goes a bit more in depth about like what this means and how these neural network architectures work. And I take them a bit like as a given here because it would be too much to cover it all. But I hope this was helpful nevertheless. Is there like a follow-up question, or I just always see like the number going up?
No worries.
Yeah.
I was just sending the link for last year courses. So.
Yeah, perfect. Right. So, like with this function, we basically can now generate neural networks that can work as a generator because we have like this noise dimension as the input and the data dimension as the output of arbitrary depth and width, so that we can experiment with it. So if we have this function, we can now initialize a generator net. And here I keep it fairly simple. So a noise dimension will be just like a vector of two independent draws from a standard normal distribution. So it will, for each generated fake example, we will take as an input like a vector of two draws of independent normals. The data dimension is just x and y, right? We just have those two dimensions. And like this is, yeah, like it's a medium-sized neural network with two hidden layers and 128 neurons per layer here. So in total, and we can look at what this like call to this function and generating this GNet object here generates, and this is now an NN module, so that's like a torch neural network module that has 17,154 parameters that we can now train. So that's like, yeah, like it's more than in our typical like logic regression models, but like not like a massively huge neural net with like millions of parameters. Then we can do the same thing for the discriminator, and here like the discriminator looks more like classical neural nets that you might have come across, because it is basically a classical neural net that tries to predict labels, right? So like tries to discriminate between fake and real, so that's the labels, and takes as an input like our data, and we will later in the training we'll make sure that it looks at fake data and real data, and then uses that to learn like to distinguish between the two. So again, like this, the input dimension to this neural network should be the data dimension. We don't need to specify an output dimension because that will just be one, as it is just like a two-class prediction problem. And we will need to add, like for this classical GAN value function that we looked at, where we use the log of those discriminator scores, right? Which comes from like this binary cross entropy formulation, or like from standard logistic regression. We need to make sure that the output of our discriminator net is probabilities between 0 and 1. And one way to do that is to use a sigmoid activation function after the output layer, right? So it will be like output of dimension 1, and using like this sigmoid activation, we force like the output, like each individual basically prediction for like fake and real samples to be like a prediction of a predicted probability of being fake. So like the sigmoid function squashes like the real valued output. So this is basically logit scores to like the 0 to the interval between 0 and 1, so that we actually get probabilities. And we will later see other GAN value functions, other GAN architectures where this we don't necessarily need this anymore, where like the discriminator works a bit differently and uses like real valued input for the value function. And therefore, we can also switch this off, like if we want just the output of the linear output layer. And like in this example, I basically mirror the architecture of the generator in the discriminator as well. So it has the same number of hidden layers and hidden units. And this sort of like became the convention in GANs, like that the generator and the discriminator are basically mirrors of each other, as it like just works well empirically, and also ensures that like one network doesn't overpower the other network. Because like to learn this adversarial game, we want both of those players to be of similar power, right? Because otherwise, like if one can learn faster than the other and overpowers the other, then we probably wouldn't get to the equilibrium. Like the discriminator network now has 17,025 parameters. Does anyone have an idea why like this is like about 150 parameters less than in the generator network? 130. It's just a quick knowledge check. Yeah, that's I can see the answer in the chat, because only one dimension, I don't know, it's like the answer / question in the answer, but that's exactly right. So in the generator, we have like 2 input features and 2 output features. And in the discriminator, we have 2 input features, and as we could see here, only 1 output feature. So like the last layer will have less parameters than in the generator. So this explains like this tiny difference here. But of course, this means like if we have like data with more dimensions and like depending on how we choose our noise dimension, like the difference in the two could be larger. All right, then we need optimizers for both of these networks. And here I just choose like the Atom optimizer from the PyTorch library with like standard momentum parameters. And we need to tell it which parameters like this one should optimize, and for the step to update the generator, we only want to look at the generator parameters, and we need to set a learning rate. And this is like a very small learning rate that also makes sure that like those two networks don't overpower each other too quickly and make like huge jumps in like different directions. And use in this example the exact same optimizer on the discriminator net parameters, and just call them goptim and doptim, that we will then use in our training group to update like this adversarial game. And now we are at like the exciting step where we can put this all together, like what we like this game between bandits and police, the formula, and the networks that we set up to actually make one run of the game. So to make one run of the game, like we first sample a mini batch from our real data. So here we use our like toy data that we transform to like this torch tensor object, and sample like this sample command in R says that we want to sample like basically 64 indices from like 1,000 potential indices, and then use those indices to pass like a mini batch of actual real data. Then we sample new noise, and torch rand is sampling from a standard normal distribution with the given dimensions. So we make sure that like the mini batch size, we use 64 here, matches like the mini batch size from the real data, and our noise dimension is here. So this will directly sample like a torch tensor object with dimensions 64 by 2. So you can think of it as a matrix with 64 rows and 2 columns. And in each of those cells is just an independent draw from a standard normal distribution. Using that, we can now use our generator to generate fake data, right? Like we pass like this noise, that's exactly what we saw in this picture, as input to the generator net, and the output of that is fake data. As like in the first half of like this update step, we only update the discriminator. We don't need a gradient here, so this just is like for efficiency reasons that we don't calculate gradients for something that we don't actually need here. Like get a tensor, a torch tensor back like that holds fake data. So in the first round, and like we will run through the first round, like through this code chunk in a bit. This, of course, is like the bandits who have never seen money trying to come up with something they think is money. So this will not look like anything close to the real data, right? So in the first round, this will look like random noise as well, typically. Then we use our discriminator net to calculate the scores, so the probabilities of being real on the real data and on the fake data. So doing this separately on those two sets of data allows us to calculate the loss in a way where we don't actually need to append labels as well. And this is basically exactly the value function that you've seen on the slide. So this is the original GAN value function, where we now use the log of those predicted probabilities of being real for real examples, and add the log of 1 minus the probabilities of fake examples being classified as fake. And as we want to, as the discriminator wants to minimize this, we just use the negative mean of that. So this will be a vector, right? So this is a vector of 64 scores. This is a vector of 64 scores. So this adding this up was like a vector of 64 scores. And now taking the mean of that and putting the minus sign in front of it, make sure that we minimize this portion of the loss. So we calculate the loss. So this is just a scalar. So that's just a value, a number, because we just average across this a vector and take the negative of it. So this is how in Torch, PyTorch, or Torch in R, one update step looks like. So we first zero all the gradients so that we don't have weird accumulating gradients over time. So we are only interested in the gradient at this step. Pass the loss backward through the network. And again, if you don't know what back propagation means in neural networks, you're very welcome to dive into the video of last year's summer school on neural nets. And when we calculated basically the gradient update for every neuron, for every parameter in our neural net, we can then take a step in that direction using our optimizer. And like that, we updated our discriminator for one step. In classical neural networks, this would be it. We would put this into a loop, right? And then try to minimize this loss until we get the best prediction between real and fake. But here we have this adversarial game, right? So this is only the first half of an update step of a GAN. We also need to take care of the generator now. To do that, we sample a new batch of noise, generate a new batch of fake data. And we actually only need fake data in this step because the parameters of the generator network only depend on fake data, right? In the formulation, if you look at the real data, there is no G around there anywhere. Then we calculate the discriminator score for fake data, then just take the second portion. So actually we want to maximize this whole thing, but this first bit doesn't depend on the generator at all. So we can drop it out and just maximize the second portion of it. And calculate now, since we want to maximize it, the positive mean of that, and then take one update step for the parameters of the generator, where we also zero out the gradients first, pass the loss backward and then take a step of our optimizer in the right direction. All right, so let's just run this one step for now so that we can actually use our generator net to look at some synthetic data after the first step. So we basically now, by running this code chunk, trained our first GAN for one step on 64 examples, like a mini batch of 64 real examples and 64 fake examples. And now we can just use our generator net to produce synthetic data, right? So we just pass noise through the generator net, and this torch S array makes sure that we get back an R object instead of a torch tensor, so that we then can have a look at it and plot our synthetic data after the first step. Here I will use a different noise vector than in the training. Like this will just be a fixed noise vector, like drawn from the same noise distribution, but also with 1,000 examples, so that we get as many fake points as we had real points. And then we can just plot this in the same scatter plot as we had before. And of course, like you remember, like for the real data, we had like this parabola around, like the minimum around 0, and then like it was going up to like 8 and 9 and 10. So this doesn't look like anything like the real data yet, right? So this is just after the first step, pretty much random what this will look like. So what do we need to do now? We, of course, need to train this for longer so that we can actually get closer and closer to this equilibrium, or in the best case, even reach an equilibrium state between the generator and the discriminator, where like they don't update each other anymore. So where they basically are in a stable state where the generator samples something that looks like coming from the true data distribution. So we will do this now for 3,000 times. And after every 100th step, we will look at the progress of our training to observe. And since we observe the training along the way. And there's like a great question in the chat I just saw in the corner of my eyes. So should everyone have a random plot since we haven't set a seed? That is exactly correct. Like we haven't set a seed for torch, like for this draw here. So that's different for everyone. And we haven't set a seed also for the initial state of the networks. So this will look different for everyone. However, the training should nevertheless behave similar for everyone as well. What happens here in this loop now is like the update step that we just walked through, right? Like those two parts, first update the discriminator, then update the generator, are just repeated like 3,000 times. And then we added like this getting synthetic data and plotting it after every 100th step so that we can observe training. So that's really from scratch. And this now will take some time. And we should get some plots soon after every 100th step.
Marcelo, there's a couple questions in the meantime. So
yeah.
There was someone was asking, there is an error of G_net not found. So which means that probably that object was not created. So right. Can you maybe like help with that? Like what can produce that error? And another question is, how about TensorFlow keras? I'm not sure what exactly is the question about TensorFlow and keras, but if the question writer wants to ask out loud, please do. Yeah.
So the first thing, so yeah, that as Olga said, this probably means that like the GNet wasn't created before calling it in the like this training step. So just make sure that like everything is run in order, so that like it can actually access like those objects when they're needed. And if it doesn't, just go back up like to wherever GNet is created and start from there again and run the whole sequence again. How about TensorFlow or Keras in place of PyTorch? Yes, of course. Like you can use whatever favorite neural network API or even your own neural networks in place of that, right? So what you would need to swap out is probably how you define those networks. So using like the Keras or TensorFlow API instead of that. And like then calculating the loss and backpropagation is very similar. You would need to use TensorFlow functions here instead of torch functions. Just make sure that you actually use functions from the neural network API that you work with, so that like all the gradients are calculated. Like you couldn't use like just the base R log here, for example, or in Python, it is often compatible with like a NumPy log, but like it would be very similar in principle. And then the update step might look a bit different as well. But it's very similar. So like if you want to do this from scratch as well, like you basically just have to make sure that like the right networks are in the right places and that you calculate the loss in a way that the gradient is calculated in the network API that you want to use. But I don't have now like code for this in TensorFlow or Keras, if that's what you were hoping. But it would be perfectly like translatable. All right, let's look at like what our network does actually. So we see after 100 steps, it gets like the parabola already, which is great, but then like flips it around a bit. This looks weird. Let's see where we are. It actually ran for the 3,000 steps already. And we can see like that around like step 1,400, 1,500, it starts to produce something that at least looks like in the similar domain as our original data. And then this gets better and better. Hopefully it does. So that after the 3,000 steps we ran it for now, we have something that looks very much like the parabola that we had. To actually see that in one plot, we can combine those two data sets, so the real data and the fake data, into one plot, and we can see that it's actually pretty good. Like there's still some noisy points inside the parabola here, and like it might be a bit off here, but like this might get better and better if we trained it for longer. So now we also tracked like those two different losses, right? So this is what you would typically, sorry for the scrolling here. So those two objects here, where we at each iteration just stored the loss into a vector. And here again. So with like traditional machine learning or traditional neural networks, what we would like to see is like a decreasing loss curve, right? Like we would like to see that this approaches a minimum and then stays stable at the minimum. Here we will see something very different because we have like this adversarial nature, like this game where those two networks are pitted against each other. So the first plot will just be the like a line chart of the discriminator losses, and the second one will be a line chart of the generator losses. And we will see that this doesn't have like this nice shape of like where we have a nice like decreasing curve, as we probably know them from like a lot of machine learning models. But what we see, like if you remember, around step 1,400, 1,500, the generated synthetic data looked almost in the right domain already, and then better and better. So what we can see is basically that here, like those two networks really fight against each other, right? Take one step in this direction, another step in the other direction. And then it starts to stabilize around like the step 1,400, 1,500 for me in this example, and stays rather stable there. And this is like also when we like see that like the quality, let's just go back to this step 1,400, 500, like starts to improve also. Like one problem with those GANs is like from those loss curves, other than with like traditional machine learning or neural network models, we have no direct way of assessing like the quality of like the generated data there. So like it's therefore also hard to come up with like early stopping rules or like trying to figure out when to stop training. Like, yeah, like the best heuristic we have here in this traditional GAN framework is to see whether like this discriminator loss stabilizes to some extent. And now you could, of course, continue training, right? Like we could just rerun this, and then like it would start with the like the last step that we had before. Like this is all stored in the state is stored in those networks. So you could continue training and see whether, and it probably will improve the synthetic data even further. However, I'm satisfied with like satisfied with this outcome. Like, and I hope you are too. Like, I hope that you can see how like these two networks and this training loop that we coded from scratch produced a generative adversarial network that we can use to learn like this two-dimensional, rather simple, but still like not trivial distribution, and actually sample new synthetic points from that. So because like this is of course very laborious and you don't want to do this every time again, I coded up a little R package that makes your life a lot easier. So basically here's 4 lines how to achieve the same result here, where we get like the generator, and it's exactly the same function that you've seen above. From the package, the discriminator from the package, and then you can just pass the data, the noise dimension, and the generator net and the discriminator net to a GAN trainer function that will take care of everything else. And you can also generate those intermediate plots. So that package also tells you how long training will last, which is not that interesting in our example right now, because it's rather quick, but it will be very interesting as soon as we look at image data and maybe don't have a GPU available. This default option of the GAN trainer uses some slightly optimized design choices that we will cover later. So the intermediary steps will look a bit different, but in the end, like after those 2 minutes, what we should see is that we will get synthetic data that looks like it could be drawn from the real data. So at 35%. So that's a good time to ask questions. And I see one in the chat, like, why does the loss not give us information about data quality? That's a good question, and it's like hard to answer. But essentially, what we model here is not data quality directly, right? Like we model like a game, adversarial game between two actors that try to reach an equilibrium. And we know from theory that in the equilibrium, we should get like perfect data, or perfect draws from the underlying data distribution, but like we don't model data quality directly. And in classical neural networks, classical machine learning for prediction, like we directly model, like the loss directly models how good we are at predicting. And therefore we can use directly this loss for like maybe like early stopping, figuring out like good points from the loss curve when to stop training. And in the classical GAN, this is not possible. Like all we get is like a feeling about whether we are close or in an equilibrium, but it doesn't tell us whether it's actually the equilibrium. However, there is some like modifications to the value function that allow us to actually directly interpret the losses that we get as some sort of quality indicator. So like that's only true for the classical original GAN. But like there's improvements that will allow us to get a score that is correlated with quality, so that we can then actually also from those scores infer whether you generate good data. So this training is finished, and we can look at the real and synthetic data as before. And so this is just an example how with the RGAN package, it's a lot easier to train your GAN and to look at it. So like there's 2 more questions in the chat that I will try to answer. So the first one is, if you would use a GAN to obfuscate privacy sensitive data, would you change the objective to, e.g., come as close as possible to the original regression results stated in your paper? That's a good suggestion, and like that's a good way to incorporate like potentially measures you care about. However, it has the downside that you basically encode those models into your generative model as well. And if you use GANs, and especially for synthetic data that you want to pass along to other researchers, maybe where you don't necessarily know ahead of time what kind of analyses they would like to run, this is probably not what you want, right? If you know exactly that you want to run this regression or the set of regressions, then this would make sense, and this should also improve the utility for those tasks, as you will directly minimize or maximize like this loss when learning the GAN. But then the question is, why would you need a generative model at all? Like, couldn't you just learn like those regressions privately on the original data and then report those regression coefficients if that's all you care about? So I guess this is like a trade-off of like the GAN being trying to be as general as possible, like also learning relationships in the data that you don't explicitly want to encode. Of course, with the GAN loss, you also encode implicitly some relationships that you care about. And at the same time, having high utility for a specific task. Like if the goal was just to be accurate on those tasks, it would make a lot of sense to add this to the value function in some way. But the goal with like privacy protective synthetic data is to allow more analyses that you maybe don't even know about, like that downstream users can choose. And then there's a second question. Could you quickly explain the dropout rate again? And are there any cases where noise dim should be different from data dim? So two questions actually, and both of them very good. So dropout basically is a way to get additional noise uncertainty into the networks. Let me just scroll up. Sorry for the quick scrolling. And what dropout does, it randomly sets, or basically it randomly takes out, like crosses out at each iteration a pre-specified percentage of neurons in that layer. So those neurons that are just like switched off, basically, oops. And this happens at random, don't contribute to like the prediction or to the generation of synthetic data in this particular step. However, they still need to learn something, or they will learn something because they are not switched off in every round, right? So basically you have like only a random subset of all the neurons available at each training step. And what this helps is that helps against overfitting, because like basically all neurons have to learn to generalize in some way, right? And in combination, they cannot specialize on like one feature, one point. It's harder to overfit. And and we will do an experiment with dropout later in the second half, also allows us to quantify the model uncertainty of neural networks to some extent, which will allow us to sample better from the underlying distribution. Because as you can see, after those 3,000 steps, right? Like we basically get something that looks like on a regression line, right? Like as if we were predicting with like a linear regression model and not caring about the like noise in the data. So like if we train this for longer, they will line up even more and more. So on average, each fake point will be a pretty good representation of the underlying function. But we lack like fidelity, like diversity in those generated examples. So therefore, this dropout when using to generate synthetic examples can help to get like a more diverse like synthetic data as well. The second question, and are there any cases where noise dim should be different from data dim? Yes, like we will see those as well later. So this is just coincidence here, and like to keep the initial network rather small. And it is also sufficient in this problem, like this function can be represented in a two-dimensional space. So basically the noise dimension restricts your latent feature space, like how many dimensions your latent feature space can have. And for images, for example, like the data dimension can be really huge, right? Like if you think of like a 64 by 64 pixel image that is 64 by 64 features, 64 times 64. So that's a lot of features, but you would expect that like the feature space, like this latent space from which we learn like to map new images has fewer dimensions than like this. So then the noise dimension would be typically less than the like data dimension. And if you use convolutional neural networks, the data dimension will look a bit different. Like we will have like 3-dimensional tensors as the data dimension. And then there is another question about, I will just read it again. Can we use CUDA or other parallel computing packages to speed up our GAN training for large amounts of data? Yes, that's the beauty of Torch and also Keras and TensorFlow. It will work with GPU as well. And also the R package will work with the GPU if you have one. Unfortunately, and I just figured this out this morning, like the Colab instance doesn't have the right version of CUDA installed. Like I will show you the CUDA speed up on my machine later. But yes, this is definitely possible. And the speed ups are typically the largest if you work with like higher dimensional data, like images and, for example, deep convolutional neural nets, as we will see later. So training in the Colab notebook will take about 4 hours for one epoch, whereas on the GPU it will be just like somewhere between 15 and 18 minutes. So that is a huge speed up, and certainly possible with like the pipeline that we have here. How to increase accuracy and speed of GAN? Accuracy is maybe the wrong goal here, but like if you cross out accuracy through quality of synthetic samples, I can try to answer this question. So a lot comes from like different design choices that we will look at. So there's many different ways of how to optimize your GAN pipeline or your GAN, and tailor it to a specific use case that you might have in mind. So a GAN for an image will look very different from the simple GAN that we had here. And speed, yeah, that's like hard. So that of course depends on the kind of networks you want to use. And like the biggest speed up is probably if you work with images and deep convolutional neural nets, having more GPUs available. But that of course often crosses like with a budget constraint. Like the last question is a very interesting one. If you have a low accuracy of the data at the start, would it be possible that the GAN training slows down and doesn't run at all? Yeah, with different architectures, or like also with this architecture, you can have cases where you have vanishing gradients. Like if the discriminator, for example, is very bad, like and underpowered, and doesn't learn anything and just says anything it sees, it's 50-50 real or fake. That would be a case where like the whole network system couldn't learn at all, right? Yeah, like that can certainly happen, and like you can try to find an example in this workbook where this happens. And then I guess trying to find strategies to like identify this during training would be super helpful to not like get stuck in a long training there at all. But in general, like the hyperparameter and architecture optimization of GANs is like a very, very open research field and like the current research frontier. So it's hard, right? Because there's so many moving parts and it's not even clear what we optimize for. Or it is clear implicitly, we want better quality of synthetic data, but like how to define this mathematically is not always easy. And then trying to optimize this for speed and accuracy, and like maybe also kick out bad runs early on is definitely worthwhile. And I hope like that the second part will answer some more of that, and I can point you in the right directions there. Are there any more questions for now?
There's one on YouTube. I'm just going to read it out loud if that's okay. Do you know about the performance of GANs to fill missing data in multivariate time series data sets versus more common procedures like multivariate imputation by chain equations?
Great open research field again. So I have looked at the context of multiple, in the context of imputation, data imputation, multiple imputation with like cross-sectional data, but not evaluated it in the case of time series data. In the case of cross-sectional data, it really depends on the underlying data structure, right? Those, especially those chained equations, can do a pretty good job, especially in combination with like predictive mean matching. Really hard to beat, but like as soon as you get like, and I would argue that this is most often the case in real data applications where you don't know exactly what kind of underlying like correlations and influences you have. GANs can pick up better like those weird cases. And I would assume that something similar is true for time series data. However, like for time series data, like the GAN architecture would need to take into account like this time series structure of the data as well. So one way to do this could, for example, be using like recurrent neural networks or also convolutional neural networks, so that you make use of the structure that you have in your data. So like the architecture that we have here wouldn't probably be very helpful for time series data at all. And this is maybe before we break for a little bit, one big takeaway that I think that everyone should take out of here as well is that like generative adversarial nets are really more like a framework where you can have many, many different forms, many, many different architectures for many different problems. And it's not just like one model, right? It's not like logic regression, like there is one model and then you try to do one task with it. Like it is really a framework that is built around like this idea of this adversarial game, and then depending on what kind of data you want to synthesize, what your exact goal is, you need to like build your own model within that framework. So there is like endless possibilities, endless combinations, and I would assume that there is like also a good way to impute time series data, but like to find that model is hard. All right. But thank you for all the great questions. And at this point, I would like close like the first part of like the generative adversarial net course and break for like 15 minutes. I guess I need to get some water that my voice can keep going. I will see you all back at 12:15 Central European Summer Time. So in exactly 15 minutes. All right, welcome back, everyone. I hope you could use the break as well as I did. Like, drink a lot of water. And now that we have like a good overview of like the basics of a GAN, we coded one ourselves, and we have seen in the code and also especially in the questions around it that there is like a lot of things that we need to think about, right? We needed to think about like the network architecture. We needed to think about the value function, and I hinted at like that there is different other value functions that also allow us to interpret like the loss, or like what we can see as a quality indicator. Then there is different optimizers potentially. Then there is different, we had this question in the beginning, different noise distributions that we could pass to the generator, and so on and so on. So basically at every step along the way, we can make different choices. And this again speaks to the fact that like generative adversarial nets are, or how I like to think about them, is really as a framework of many different models that then can be used to achieve very different things, like from synthesizing images, as we've seen like in the introduction, to synthesizing speech. Those networks, those GANs will look very different to synthesizing tabular data or even time series data. So let's, in this next bit, talk a bit about those design choices. So the next bit will be mainly about those design choices, and then we will have two little workbook exercises. One where we will look in depth on dropout in the generation of synthetic data and how this might help to generate more realistic data. And then, of course, like we try to build a GAN that can produce fake images. So I guess, or I hope at least some of you came for synthesizing images, and like this basic simple example was really just to get a good understanding around like what's actually going on. All right, so in those design choices, let's start like with the one that I also started with, like, or the whole GAN framework is basically built around this idea of this adversarial game and this value function of trying to the discriminator trying to predict what's real and what's fake, and then the generator trying to maximize this, and the discriminator trying to minimize this. There is, and yeah, this is probably the most, or one of the more important choices in a GAN. And I really like the original GAN value function, especially to introduce new people like you to generative adversarial nets, because it has like this intuitive formulation of like this trying to predict what's real and what's fake. However, it turns out that like if the discriminator is very good at distinguishing between real and fake data, it is really hard to learn. And also if it's like too weak, but like if it's really good at distinguishing between real and fake, we will get something that is known as vanishing gradients in machine learning and neural networks. Like if you think of like the sigmoid curve, and if you get like predictions that are very close to 0 and very close to 1, the slope of the loss function at those points is very close to 0. So that means that like if we backpropagate like the loss, or like the gradient of the loss, this means that like as the gradient is the slope of that function at this point, would mean that we would make tiny update steps, if any at all. And this means that like if we have like a discriminator that is very good at predicting zeros and ones, like what's fake and what's real, then we can get stuck there, and the generator just doesn't learn anything useful anymore. And this is of course not what we like, because this doesn't get us any closer to the equilibrium that we like to find. So therefore, like the researchers proposed a new value function a couple of years after the original GAN. And it's also a very influential paper in the GAN literature, and like it's linked, like all the papers are linked directly in the presentation. So if you want to have a look at it, you can click on it and you'll find the paper right away. Propose an alternative value function based on the Wasserstein distance. Or maybe some of you have heard from like the Earth mover's distance, which is a measure of how far apart two probability distributions are, basically. And the intuitive idea there is like how much Earth do you have to move from, like if you think of those distributions as piles of dirt, how much dirt do you have to move to get from like the first to the second distribution. And this turns out like swapping out like the JS divergence, which is the, like if you reformulate the original GAN function, you can see that it's basically using the JS Jensen-Shannon divergence between two probability distributions, like using the Wasserstein distance there instead of the JS divergence, has some very desirable properties. And in particular, the first one is that it has like it gets rid of this vanishing gradient problem, because we don't need the sigmoid function anymore. Like we can just use the linear output layer in the discriminator. Therefore, this leads to better results, or more consistent results as well. And another nice feature is that like we can interpret this Wasserstein distance between those fake and real scores as it is correlated with quality of the produced synthetic data as well. And so basically, this leads to the following value function. It's a lot simpler even than the original one. So remember, before we had the expectation of the log of the discriminator scores plus the expectation of the log of 1 minus the discriminator scores on generated samples. And now this reduces to, like if you use the Wasserstein distance here, to the expectation of discriminator scores on real data minus the expectation of discriminator scores on fake examples. However, this comes with like one, as we work on the on real value discriminator output now, like this comes with that downside, namely that the discriminator needs to be a Lipschitz continuous function with a Lipschitz constant smaller or equal to 1. This is needed that this value function can converge to an equilibrium, and we don't, we basically constrained the space in which we look for an equilibrium. In practice, this can be achieved by clipping the weights of the discriminator to some pre-specified range, for example, minus 0.01 to 0.01, and making sure that all the weights after updates are in this range. So this will constrain this to like such a space. Other alternatives are you can also use like a gradient penalty on the Wasserstein value function that also ensures automatically that this property is met here, that this value function is Lipschitz continuous. Then there's some more recent work on value functions that try to bridge or like try to use other divergences as well, like KL divergences or in general F divergences, and bridge GANs in this whole space of potential divergences between those probability distributions. So we have like those two probability distributions, and this seems to be particular promising paper that comes up with a new value function that also gives more stability in training, and also gives you a loss or a value, the values of the losses that are correlated with quality of data examples. So basically, this is directly addressing some of the questions we had earlier. So there is ways to like improve on this original GAN functions, and this work so far basically came from addressing weaknesses on the computation math side of the original GAN value function, like the vanishing gradient problem. However, like what I think might be a promising research avenue that like if you're interested in finding better value functions is exactly what was suggested in one of the questions before as well. Like depending on the goal you have with your GAN, for example, if you want to generate synthetic data that's particularly good for some regression model, you can use that information to inform your value function, right? Like you can tailor your value function to the problem that you want to solve. And informing those value functions with like background knowledge in, for example, the social sciences or data science, like maybe even theoretically grounded in what kind of properties you want to achieve for your synthetic data is, I think, like a very promising direction of where like GAN research with like applied research in like subfields could merge. So that's the first thing, and like as I've said, like we don't need like this sigmoid activation function in the output layer of the discriminator anymore in this case, and we can just use the linear output layer. So putting values on the real line. In those GANs, like if you read up on those papers that use like the Wasserstein value function, the discriminator is often called a critique instead of a discriminator or critic, as it's not actually discriminating between real and fake examples anymore. It's trying to criticize them like on a continuous scale and trying to find like the like way that like those two distributions match. So that's the first choice you typically can make, and in the RGAN package you can choose like the original value function, the Wasserstein value function, and also this KL divergence based value function by Song and Ehrman pretty easily, and this makes it then easy to try to see what those choices, like how they impact your synthetic data in the end. So that's the first important choice you need to make, like what kind of value function, like what kind of game are those two networks playing. Then the second important choice, and we have also implicitly made that in the first from scratch example, is choosing suitable network architecture for both the generator and the discriminator / critique. And parts of that network architecture, in particular of the output layer of the discriminator, depend on the chosen value function. So if we want to work with the original GAN value function, we need to have like some transformation to like those probabilities in the output layer. Whereas in the Wasserstein GAN, like if you choose the Wasserstein value function, you can have like a linear output layer. So this influences already like your network architecture. However, there is like more choices than just like the output layer, right? Like we talked about width and depth, and then also about potential different architectures of those hidden layers. In general, it is important that the discriminator or critic has enough capacity for whatever problem you want to solve, and where the meaning of enough capacity is heavily dependent on the application that you want to solve. So in practice, for example, for image synthesization, convolutional neural networks achieve the best results, which is pretty much in line with like what we know from computer vision, and like what kinds of network architectures work well also to do like object recognition in images, for example. So like if you want to work with images, you would probably need to look into convolutional neural network architectures. And like if you follow that link of like this person does not exist.com to like the original StyleGAN 2 implementation, you will see that this is a huge convolutional network with like skip connections and residual connections, and like just a huge convolutional network. If you, and we had this problem with like, for example, imputing time series, or like if you don't even want to impute, but generate synthetic time series, recurrent neural network architectures are sensible choices. And if you remember like the speech synthesization problem or example in the intro, like speech or text is can also be thought of as like time series, or videos as well. So for those kinds of problems, like those recurrent neural network architectures are typical sensible choices, where you make use of like the time structure, like the structure in the data that you have at hand. And for simple cross-sectional tabular data, fully connected network architectures are usually sufficient, with the exception of data of mixed types. So like if, for example, you have like, and I know this as a political scientist, this is a very typical data format, that you have real valued input like categorical variables, ordered variables. So like really data of mixed type. They're like the output layer of the generator has to account for this kind of mixed data. And also like how you encode this data. So for categorical values, usually like a one-hot encoded vector makes sense, and then like to learn like one-hot encodings takes a bit more effort. Like if someone wants to read up on that, like the Gumbel softmax trick is what is very useful there. So the network architecture has a huge influence on like what you can learn, and depends a lot on the application that you have in mind. So the GAN that you will use to synthesize images will look very different to the GAN that you could use to create a synthetic data set from some data that you collect. Then like a more recent area of research is like choosing the right noise distribution. So it's really great that we had this question right in the beginning. So in most GAN applications, the noise distribution for the generator is just the standard normal distribution. And this, of course, also has practical reasons, since like in most of those neural network APIs, it is easy to sample from independent standard normals. For images, as I said, sometimes uniform distribution on the interval -1 to 1 is used, especially if you normalize your pixel values also to lie in that -1, 1 interval, so that you then can have like this nice gray and black and white noise image basically as an input as well. However, there is recent research that shows that the choice of the noise distribution heavily influences the behavior of GAN training, and in particular, this Huster et al. Paper is very interesting for social scientists and I guess data scientists of any like flavor. They show that like it is very hard for GANs with like a standard normal noise distribution to learn heavily skewed data. And as a social scientist, like I come across skewed data quite often. Just think of like income, for example, or also firm sizes, like more like an economy, or also like in elections, the number of one seats is very skewed towards like bigger parties that traditionally did well. So if we would want to synthesize skewed data like that, they show that this is really, really hard with a standard normal because it has like those flat tails, and therefore it is very unlikely to sample like outliers in the latent space. And for skewed distributions, especially if it's like a log normal distribution, we need like heavy outliers to learn the distribution well. So they show that using a Pareto distribution instead of the standard normal helps with that. So that's the distribution that has fatter tails. And I guess a lot of like work in classical statistics could influence those choices of the noise distribution as well, like thinking about like what distribution transforms well into like the target distribution that we have in mind might be very helpful there. And then a very recent paper by Yang et al. Shows that in the context of image or high quality image generation, that like this can be improved by leveraging hubness of the noise distribution. So what does this mean? It means that like in your standard normal ball, like if it's or like some higher dimensional object, not every point in this sphere, or like if we have like a two-dimensional space, not every point in that pixelated noise image is as likely to produce a high quality image as any other. So, and they show that like there is hubs of like good quality noise priors, and that like neighbors of those hubs, and you can identify those hubs, so it's basically thinking of like this noise sphere as a network. And neighbors of those hubs also have a higher likelihood of producing a high quality image, whereas just random sampling will give you like high quality noise and low quality noise, basically. So identifying those hubs and the neighbors of those hubs generate a higher quality images, which is a nice result, and they provide an algorithm of how to identify those hubs. So like, and that, like, as you can see, like those papers are very recent. So this is pretty much like ongoing research, and it's like not, yeah, trivial to give like good advice for what the best noise distribution is, for example. So it's really dependent on the application that you have in mind, and then again, like a lot of trial and error, like what works and what doesn't. Then the next big choice, design choice that you can make in a GAN is choosing an optimization algorithm or choosing the optimization algorithms. And even though it didn't look like that, but like if you start to play around with GANs by yourself, you will see that the optimization of GANs is notoriously hard. And one reason, of course, is that we don't have like this sort of direct feedback as we have it in classical neural networks, classical machine learning, whether our training goes in the right direction or not. And on top of that, like we have an additional problem in GANs. So in our simple introductory example, and that's also what they did in the original GAN paper, they just used the same optimizer, so basically the same step size, same learning rate for the discriminator and the generator. So like one would take one step in one direction, and like the other one would take a similar step in the opposite direction, basically. And there's research that shows that like this symmetric gradient ascent descent, like because we maximize one ascent and descent, we minimize the other, might not be the best option. In particular, and this is a very cool and simple trick to implement, and very much encourage anyone to play around with that. Heusel et al. Group from Austria have shown that using two different learning rates, and they show theoretical results for that as well, for the optimization of the discriminator and generator, improves GAN training, and in some cases makes it even possible to equilibrium, whereas like this even and descent with the same learning rate fails in some cases to ever get to an equilibrium, because it will overshoot. So that's very simple to implement, like just putting like those two optimizers on two different learning rates. And this usually helps to stabilize GAN training by quite a lot. In addition to like the learning rate, like, and how to choose like the learning rates of those two different optimizers, the concrete choice of an optimizer, of course, has an influence, like whether you choose like simple as stochastic gradient descent or like those other momentum based alternatives or updates like add-on RMS prop and the like, is a choice you can make, and they behave very differently, and they have all their own hyperparameters that like those momentum terms on top of like the learning rate, and you can also tune the batch size that can also influence GAN training. For images, it has been shown that like larger batch sizes typically help in training the GAN because like it's seeing more consistent examples. I see that there is a question about noise distributions. I will just read it. Is it misguided to think that we are somehow aiming at some noise distribution that are close enough by some reasonable metric to the observed distribution, but not so close as to essentially replicate it? That's a good question. And I guess you could experiment with that. So you could, in our original example, use our toy data, like our original data, as the noise distribution and see what happens. But yeah, so basically with the noise distribution, and that's not so clear with our initial example, but clearer with like images and high dimensional data. Our goal is to figure out like a latent space, a lower dimensional than the original data, lower dimensional latent space that represents the data well. And it should be close enough in terms of like if you have, for example, and I will show an example of that, if you have like holes, if you have areas where no points are, and then you have regions where like there's a very high probability of points. If you have such holes, it would be very useful for the prior also to have some structure like that. But that, of course, again, depends a lot on like the problem at hand, like and how to come up with good priors for different problems is like an open research question. But I think like with the end of your question, like with like close enough to the observed distribution, you could run like a very cool experiment with that and see what it actually does to your like synthesized distribution. Because then essentially the network would have to learn to just pass through any input as is. And if it does that, like it would just perfectly replicate the original data. So therefore, yes, like we would like something more like a latent space representation, try to figure out like a latent space representation of the data. And if both are low dimensional, we could of course use the same as well. Then like one thing I talked about a lot already, because I think this is really interesting, is the next thing, like choosing dropout during training and generation. So in neural network architectures in general, like those dropout layers help to regularize network training because we add noise and prevent overfitting. And in classical neural networks, there's like a useful side effect of that, that like those dropout, like using dropout in prediction can be used to estimate model uncertainty of neural networks so that you can get error bars around predictions from like classical neural network predictions. In empirical GAN applications or applied GANs, there's some anecdotal evidence, like it's very good, like GitHub repo on like GAN hacks and tricks on how to train them best, linked here, shows that dropout layers also stabilize GAN training. Sorry for the second S there. Again, that's like something you could try out very easily by just adding dropout layers during training. And in classical neural networks, and what you would also do typically in GANs then is then for prediction or for data generation, you would just average across all nodes so that you basically don't have like this randomness in predictions. However, sometimes you want this, like if you want to estimate model uncertainty. And a similar thing is true for generative adversarial nets, where group Isola et al. Show and argue that dropout in the generator during data generation also provides additional stochasticity for the synthetic data generation that in turn promotes diversity of the generated data, like what I hinted at before and what I hope to show you now as well. And this very much is also still very open, many open research problems that, like, if anyone wants to embark on moving the research frontier in the generative adversarial nets and think about dropout, like the effect of dropout in GANs on produced synthetic data, especially on statistical utility, is not really researched yet, like not at all. I think this warrants definitely more research, and I will show you like a simple, quick experiment, like of why I think like that Isola et al. Are right, and like that we need to think about this more in terms of like tabular data as well. All right, are there any questions about like this design choices part, like the theoretical text heavy part at this point? Doesn't seem to be the case. Then we go to our second workbook, which is conveniently called GAN dropout, where we can use or look at like a simple experiment with dropout in, excuse me, during training and during generation/synthesization of data from a GAN. We will use the argon package here, and the toy data that comes in the argon package is exactly the same that we looked at before, that we coded ourselves. So this generates like a very similar data set. In this example, I also set seeds, and you can see that you can also control like the torch seeds. So if you just set a seed in R, this won't like set the seed to torch automatically, but you can set a seed to torch as well, so that you get consistent results. So what we will do here is we will just train like the default GAN and RGAN on the toy data, and then use like the settings of the trained GAN, and first like produce synthetic data without evaluation dropout. So the default network has a dropout during training, but this doesn't mean that we have to use it during data synthesization, and produces a sample of synthetic data without dropout during generation, and then a second time where we set like this evaluation dropout, so during generation to true. So the second synthetic data set will be generated from the same GAN, but where we have additional uncertainty from like the dropout. So this will now run for 3 minutes and train our GAN. And when we have that, we will see what I think is a very cool result. In the meantime, I just see if this, yeah, it's good. The next, preparing the next notebook. So this is now playing around with like one of those design choices, namely like dropout during generation and training. And I guess this would also be a good time to ask away any questions while we wait for our GAN to spit out some results here. Does anyone have an expectation what, I guess I gave it away before, what we will see in those two plots without dropout and dropout? Actually, no idea. Yeah, that's why we run it and we can look at it. All right, here we go. 2 more seconds. And we can look at the results. So in the left panel, in panel A, you see the results of the GAN without dropout during generation. And what you see is exactly like this, that they pretty much line up around like the function. Think of it like a regression line that we wanted to learn, right? However, that means that like we don't have, like if we use that to sample synthetic data, we won't ever get like this point or a point close to this one. We won't ever get a point close to this one, right? Because it's lacking like this model uncertainty of the GAN. Like even if we would pass different noise, they would all, like all the generated points would cluster around this line here. And typically this is not what we would want, like if we think of synthetic data, right? Especially like in this statistical sense, like we would hope to get something that looks really close to the original data. So, and like when we produce the synthetic data here in panel B with dropout during generation, that means when we pass the noise to the generator network and generate the data, we will randomly switch some of the learned parameters off. And this means we will get like slightly different results, even if we use the same noise vector every time we run it through it. And this actually promotes diversity, right? Like we see that this now gives us like data that looks actually closer to the actual data. On average, they will be the same, right? But here we have like this additional variance that is missing in this picture. So now, I guess an interesting experiment or like pushing this even further would be like how to assess quality of like such data, right? Like, because if we were just interested in like average, results, then this would be pretty good and probably even better than this one because we have higher variance here. So we need a smart way to quantify what this diversity means to us and how it contributes to quality. And to be honest, I don't have a good idea yet how to quantify this. It's not easy to also get this diversity into a score. There are two questions or three questions actually. So the first question is, does the kernel density look more similar in B? I'm not quite sure if you could elaborate on that. Would be really helpful. Not quite sure what you mean. Or at an outlier point. So you mean those getting this one? Yeah, I guess that's a good question. How that noise translates into both dimensions. And then there's a second question, or I guess more like a suggestion, how to take this further. So maybe you should consider using something like a KL divergence to quantify distributional similarity. The problem with those distributional similarity measures often is that they work well with one dimension, but it gets really hard in multiple dimensions. So the Wasserstein distance, for example, for one-dimensional problems is very well defined, but it's very hard to assess distributional similarity in more than one dimension. And beyond that, you run into the curse of dimensionality, and it almost becomes impossible to calculate any useful measures. But yes, so quantifying distributional similarity would be a good start here. I agree. And now back to the first question about kernel density plots. If I create a kernel density plot of the original data, assume the points on the regression line are more common and would have higher density. Yeah, that's right. In the best case, good question. So the without dropout model would probably converge to those high density points, right? Because it just is more likely to be there. And here, in the best case, I guess, the kernel density should look similar of the generated and the original data to have good utility, whatever that means. And this, I agree, would probably be better represented by the model with dropout, because here we would have if we ran a kernel density on the yellow points, we would have regions where we definitely observe purple points, but would have a very, very low probability of observing a yellow point. Right, but that's two great questions or suggestions, and I encourage anyone if you're interested, if you're hooked by generative adversarial networks, to explore and go down that direction, read up the literature, and I'm pretty sure that you can find areas where you could make very interesting contributions with like even like small experiments like this, and thinking principled about like what's going on, what's the relationship there. All right, so now we get to the point where we try to generate fake images as well. And along the way, we can talk about like what different design choices and even design choices that we have not really talked about, we can make there as well. So what we will do is we will run like a GAN on the celeb A. So it's an annotated data set of celebrity images, like portrait images, that is widely used in computer vision and especially GANs, because it has a lot of faces of publicly available images that we will download to our Colab environment here. And then we will use the Torch Vision package. That's, again, the same as the Torch Vision API in Python, where we can then use the image folder or use the image folder to create like our data set, where we can then sample mini batches from. And like with images, if some of you have worked with images before, you have additional problems, right? Like, because especially if it's like public collections of images, rarely do those images all come in the same size. However, for our GAN architecture, we expect all images to be of exactly the same dimensions, right? So that we can have like one GAN architecture that is fixed across images. So to achieve that, we before we load a mini batch, we need to make some transformations on the image, where we first transform it to a tensor. That's similar to what we had to do in the tabular data example. Then we resize it to like a 64 by 64 pixel image, and want to do the crop on the center. And then we normalize the channels so that we can have like good properties of the pixels, so that we work in a space of like -1 to 1. And we can then use this to transform it back to actually produce the images. Here, there was a question that came up earlier. We can look for a CUDA device, like a GPU, if we have one, and use that, and it will make a difference on this example, for sure. And we'll fall back to the CPU otherwise. Unfortunately, currently the Colab CUDA version doesn't match with the Torch requirements for CUDA. So unfortunately, we can only train on a CPU here. But I hope that those match at some point in time again. And this should be possible also in Colab again. But in the meantime, if you have access to a GPU, this would be sufficient. Like if you have CUDA installed properly and install Torch with CUDA installed, then this would be sufficient to choose the GPU to train on. Another thing that came up before, here we will choose a noise dimension of 100. So like each image will be produced from like a vector of 100 independent draws from a normal distribution. And we will now use the DC GAN architecture for the generator and the discriminator, which is acronym for deep convolutional GAN. So this just uses several layers deep convolutional modules, so that, yeah, like it was one of the first GANs that produced nice looking images, and is simple to implement and to train as well. So that's why I chose that here. And then we need those optimizers again. And here I chose like the hyperparameters from the original GAN paper. So I didn't do any additional optimization for that. But they seem to work pretty well. So we use the same learning rate here still. And the momentum hyperparameters as described by the authors of the GAN paper. And then to sample the noise, we actually need to produce a 4-dimensional tensor so that it works with this convolutional architecture. Even though we actually only use 2 dimensions, we still need like 4 or basically 3 channels for each image. We will sample that from like a standard normal distribution. The betas in Optim Adam, like that's 2 separate hyperparameters. They're both called beta 1 and beta 2. And they basically define the momentum like of the optimizer. The defaults are 0.9 and 0.99, and for some reason, like the authors of the GAN paper figured out that 0.5 and 0.999 worked better, but it has nothing to do with like confidence intervals or alpha or beta levels. It's really just hyperparameters of the like Adam optimizer. And they are called differently in other implementations as well. Bit confusing sometimes. So now we can pass all of this, like our data set, our noise dimension, like that we want to sample from a normal noise distribution. Now we have to say we are working on images. We will use the Wasserstein value function here, pass our GAN network architecture for the generator and the discriminator and our defined optimizers in here, and work on a fairly large batch size of 128 images, and only run this for one epoch. So an epoch in machine learning is typically defined as the time or the number of steps it takes to, on average, see every example once. So in this example, we have around 40,000 images and use like a batch size of 128. So that means that like one epoch has around 300 update steps. So we want to run, like, remember before we ran like our GAN for 3,000 steps, and it was like 2 minutes. And now we just want to run it for 300 steps. And because of like this deep convolutional network architecture and the high dimensional images and the higher dimensional noise, this will take longer. But I hope to show you that we still get to see images fairly soon. So I will just start this here now, but like I have no hope that this will run here before we have to part ways today. So because like we are working on the CPU only, this like takes fairly long for only one epoch, right? 4 hours, that's a long time. And typically you would want to run this for like 100, 150 epochs to get fairly good results. So you can see that like this is really a limiting factor here. Nevertheless, I will let this run for a bit. And in the meantime, show you, like I pre-trained this on like my own GPU and connect to that. Like I might lose the connection for a little bit, but I will be back. I promised. Can someone give like a thumbs up if that's the case? Can you hear and see me? Perfect. All right, so like I just copied the same code like to my own GPU server here. And I will actually also run it so that you can observe training in real time here. And this is like the faces like as a spoiler that you will get like after one epoch of running this kind of network. And now we will observe like after every 10th step in this one epoch, what the images look like. And with the GPU, like you can see like this drastic speed up, like it's the exact same configuration for one epoch, like 4 hours versus like 15 to 20 minutes. So this was after 10 steps, like it was fairly random. And then like after 20 steps, the colors change a bit. And then like after 30 steps already, you start to see like the outlines of faces, right? Or at least I hope you can see them too. Otherwise, I would need to look less at such pictures and try to make sense of them. But now definitely I hope that we all can agree that we can make out faces. And like after a couple of more epochs, it will still look better and better. Or steps, and then later we could increase the number of epochs. However, with this architecture, so like I again think it's really, really cool that like we can on our own machines code something up that makes something sensible, like in this case, producing faces when we want to produce faces. But you shouldn't expect to get like state-of-the-art results like the ones that we saw in the intro. Like in the paper of StyleGAN 2, like those researchers at NVIDIA, they are very transparent about the resources they used. And to find like the GAN that produced those nice high definition pictures, they state that they basically needed 52 GPU years to train. And as someone like me, like a junior researcher who has luckily access to one GPU, that would mean that like training that same GAN would actually take 52 years, right? Like if I wouldn't spin up like some server with more GPUs. And so they probably had access to 100 GPUs in parallel, so they could do the same thing in half a year. So for experimentation and getting to state-of-the-art images in particular, resources are definitely like a limiting factor. And I would be happy to talk more about that also, the consequences of that, because it basically means that if you don't have the resources, you're locked out of doing like state-of-the-art research there. But that's probably for another time. But like I'm very interested in anything around that as well, if anyone else is. All right, so now like after training like the first epoch for 15%, I hope now everyone agrees that we get to see faces. And then like this would just go on like that, and you would see in the end, after one epoch, those pictures that I showed you in the beginning here. And then if you would train it longer, they would get better and better. And if you have access to the GPU, I would definitely recommend to try this out on your own as well. All right, so let's go back to our collab, where we, in the same time, didn't even, it ran longer, didn't even train 3%. But just to show you that, what we would get here after this time, collab is a bit clunky when it comes to presenting those pictures, but they should pop up we've seen a similar picture before, right? So this also does the right thing, just as it on the in quotation marks wrong processor here for us to see quick results. All right, this again is a good time to ask questions. And while we do that, we can observe training a bit more, because this basically concludes the intro and coding part. And in the next section, I would like to show you a bit some of my own research with GANs, and especially privacy preserving synthetic data, and how this also plays into what we talked about with those design choices, and also understanding a basic GAN. All right. If that's not the case, I'm sure questions will pop up. Feel free to ask them anytime. And I'm also very happy to answer any questions via email, if something comes up when you work through the workbook by yourself, or if you rewatch the YouTube video, or go through the presentation materials again. All right, we did the experiment with dropout. We did generate fake images, although we're not quite there yet. I can have another look when this next section is over. We can talk about those advanced topics that I teased at also in the intro for a bit now. So basically, in one research project that I was participating in, our goal was to generate general purpose synthetic data for arbitrary tabular data sets that preserves the statistical properties of the original data set as good as possible, whatever that means. And this is also an open question, what this actually means, while giving formal privacy guarantees. And what does this mean? This means that during training, things have to be changed a little bit so that those formal privacy guarantees can be proven and met. The paper or the project is called Private Post-GAN Boosting, because it basically combines two ideas, private GAN training and also the post-processing of multiple GAN outputs. So in private GAN training, and it's often abbreviated by DP GAN or like some other acronyms where DP is part of the name somewhere, basically performs the same alternating optimization as the basic GAN training that we looked at for the last 3 hours. But it optimizes the discriminator under differential privacy while keeping the generator optimization the same. So why do we need to take care of the discriminator in a different way? If we want to have provable privacy guarantees, and one standard for that is differential privacy, we need to make sure that whenever we touch the original data, so our input training data set, to randomize our algorithm that touches that data. And randomize it in a way so that like the variance of that function basically is proportional to the privacy loss that we want to preserve. And where in a GAN do we actually touch the input data? And that is only during updating the discriminator, right? Like to update the generator, we just look at fake data and like at the feedback of the discriminator, of course. So indirectly, we look at real data, but never directly. And during the discriminator training, we actually look at real data. So if you think back to like the introductory example of like bandits and the police playing this game against each other, in this privacy preserving training of GANs, we basically give the police like very, very strong eyeglasses that are not like what they need, right? But that do the contrary, that they see worse than before, right? So that they can't actually look at the real money in high detail. So we add noise during the training of the discriminator so that we make sure that like original training data points cannot be leaked or only with very small probability. Intuitively, this of course means that like the feedback that the police gives to the bandits is also noisier than before, which in turn also means that like we cannot achieve the same like utility or fidelity quality of the synthetic data because the feedback is just not as good, right? But this will achieve formal privacy guarantees. And like luckily there's a very cool like method to like do private training for any machine learning model that uses some sort of stochastic gradient descent and to keep track of like how much privacy budget one spent. That was introduced by Abadi et al. It's differentially private stochastic gradient descent. So basically to train a GAN with privacy guarantees, the only thing we need to swap out is like this optimizer for the discriminator. And that's pretty cool. Like that's like one very small change. And then one problem is that like reaching the equilibrium is very hard without noise during training of the discriminator, and turns out to be even harder with noise, right? Like because the feedback is worse, and like we will maybe not even ever reach that equilibrium. However, this entire sequence of discriminators that we can observe during training, right? Like each individual discriminator, like at each step we have a slightly different discriminator, is differentially private. And so the sequence of those generators is also private. And one cool property of differential privacy, like this formal guarantee, is that whenever something is private, we can post-process as much as we want. So basically, we can post-process the sequence of discriminators to get a better mixture discriminator. And that's the goal here. So the issue is, and this will also be true for GAN training without noise, is that when GAN training fails to converge to the equilibrium, when it fails to find an equilibrium, the last generator, and that's what we used so far to generate the synthetic data, right? We just used the fully trained until this step generator network to generate data. But nothing guarantees us that the last is actually the best, right? And we don't even know which one is the best. Luckily, like the failure of convergence and the failure of the last generator does not mean that like a mixture of generators and discriminators from the previous epochs can still generate like a high quality synthetic data. And so we basically came up with a simple but very effective amplification method that takes like a collection of generators and discriminators across like all epochs, all update steps. So you need to store like those discriminators and generators, like that's like a small overhead, to produce like a more accurate generative model that takes into account like the whole sequence of generators and discriminators. So like this method takes as an input, so it doesn't really work on the GAN level, but like post-GAN, right? Like a sequence of generators from G1 to Gn, like, and N can be like the last step, or like it can also be like a different sequence, like where you only take like the tenths, every tenths or every 50th generate to save some space, and discriminator as well. Like those have to be the same from the same epochs. And then we, like each generator is actually like a generative model of the whole distribution that we try to model, but that's really hard to evaluate. So one way to do this efficiently is to approximate each generator by taking some samples, like let's say 1,000 samples. And so we get like a number of B samples that is R times N. So N is the number of generators here, and R is the samples per generator samples. That is like a space of potential good samples. And now we can continue like this zero-sum game, adversarial game, like in the post-GAN world, where we again have two players, like the synthetic data player who has like a mixture distribution phi over like this whole collection of points that should approximate like the distribution of each generator, while B to imitate the distribution px, and px is our original data, like the training data distribution given by the private data set. And the distinguisher player who uses a mixture of discriminators, like that we also have stored, to distinguish between like this new mixture distribution and the original distribution. That means like here in this step, or rather here, we have to access real data again. So we need to spend additional privacy budget here, but that's not too much as compared to the training of the privacy preserving GAN actually. So we have like this utility function that like we want to minimize from the perspective of the synthetic data player. and to maximize from the perspective of the distinguisher layer. And that's pretty much the same as like the original GAN function, right? And now we can use the multiplicative weights update rule, which is a nice algorithm. Like if you haven't heard of it, like I would encourage everyone to read up on it. It's a very basic, cool algorithm for solving zero-sum games. Very useful in lots of situations in machine learning. Find an equilibrium here and find a good mixture distribution over all of those sampled points. All right, so let's look at some results here. So here, the input data is still just two-dimensional, but a bit harder than like the parabola that we looked at. It is a mixture of 25 bivariate normal distributions and standard normal, basically rescaled for each center. And that's the real data distribution that we tried to get at. If we now would just, and like the first row here is without any privacy. That's like a GAN as we did train it before. As we can see here, like the last generator produces like sort of a grid. So it like gets like those modes pretty well, but it also dreams up like points in between. And this is due to like the noise distribution. So here, like if we would use a different noise distribution that would have like a similar structure as like our true data distribution, this would also go a long way and help us to get rid of like those points in between here. But the noise distribution here is also just like a standard normal. So pretty much a similar setup to what we looked at before. So now using like this post-GAN boosting method, basically generates like a better mixture distribution that gets rid of like those weird points that shouldn't be there, because we use like this information, like we have like a bigger distribution to choose from, and we use the information that is stored in the discriminators so that we can sample like from a better generative model. And this can then even be combined with like another method that's called discriminator rejection sampling that uses a similar idea, but without accessing training data again, to improve those results even further. Now, with privacy, like the picture looks quite different, and like the last generator doesn't look, or hardly looks like this grid or like those dots that we want to recover. And this is, of course, because like we have like those glasses on that make it really, really hard for the police to see, like to give useful feedback. And with this post-GAN boosting method, however, we can see that like this domain is recovered better, right? Like we can see the grid structure and like the domain is covered better and the grid structure emerges. And in the combination with like this DRS method, this also improves it a bit further, like by narrowing down it a bit more. Like those points, like this center is preserved very well. Such toy examples are interesting, but like rarely useful, right? Like when would we ever want to sample from something like this? And like what would we do with data after we synthesized it? So what we also did is, and like there was a question to that before, like we ran some regression models and machine learning models, typical like downstream tasks on the synthetic data, and compared whether this method improves like this downstream task accuracy or like other measures of like performance for machine learning models. So for example, we use the well-known Titanic survivor data set. I guess everyone who's ever been on Kaggle knows this data set, which has just like a bunch of like variables on each like passenger on the Titanic and whether they survived or not. And like the prediction task is to predict whether someone survived or not. And the first set of results here shows that what happens without privacy guarantees, like we generate synthetic data with a GAN, then with those different post-processing methods, and then train a classifier on the synthetic data and test it on real out-of-sample data. So that was not part of the synthesization. And we want to see how good we can like predict real Titanic survivorship based on those synthetic data examples. And it turns out that like this combination of post-GAN boosting and DRS like outperforms like all other synthetic data sets like by a lot, and even more so with privacy. And of course, again, like this is expected, right? Like the accuracy drops from the non-private synthetic data to the private data, since we again have like the police, the discriminator, who only can give noisy feedback. All right, so that was a bit like the quick run through like what one can do with GANs and like how they could be useful for classical data science / social science. And to be honest, I was a bit quicker, maybe too quick than I anticipated for this part. So we have plenty of time for Q&A, and I would be very happy to go through anything again that was too quick or that needs a bit more elaboration. If there's no questions, I can like look at those images again. And
there's
like
one more question in the chat.
Yeah. Would you use the post-processing in any case or only if there is no convergence? Like our results basically show that it helps in any case, right? Or like in the theoretical case of perfect convergence, you would probably not need it and it would probably not help much, right? However, like empirically, even without privacy and even training a very good GAN for the task, typically doesn't get you close to convergence in finite time. And you stop training at some point. And the cool thing really is that like even then you can use like this sequence of generators and discriminators to come up with a better generative model. And in the case of non-private training, there's no like hardly any additional overhead to do that. The only thing really is that you need to store like the networks after each update step, or like after each update step that you want to use in the generation of the bigger model in the end. So that will take away some disk space, but it won't necessarily slow training down or anything. And then like you just use that to run those multiplicative weight updates steps and come up with a nice generative distribution. That's a good question. Like in those examples, we didn't use any dropout. Like it was pre my dropout curiosity. So that's like the standard GAN setup. I just read the question again so that everyone who can't read it can also know what it's about. Might this not increase the risk of overfitting? And this meaning like this post-GAN boosting method, given that we intentionally use the dropout to increase variance, but then sort of average it out again in post-processing. So very good question. I have no idea. Yes, but like intuitively, yes, it would increase the risk of overfitting again. However, like as we need to access the real data with the discriminator again here, and also the generator, we probably should use dropout there as well. And then we should get like a good mixture model that also like gets the variance right. But I definitely have to try this out. So thank you for that question. Like I have no idea. I have not done it. And that, by the way, is also in general a more interesting, like philosophical or procedural question. Like in computer science, often the goal of synthetic data generation is to get as close as possible to the real data, right? So in a way, like even overfit to the real data sample that we had at hand. However, from a statistical perspective, that might not be the ideal goal. Like if we think that like this is only a sample from some other data generating process, and we want to make inferences about the other data generating process, then we would expect even more noise. And like this would definitely be overfitting to the real data and probably not too helpful to make inference about like the population. So like it's always an important question, like if you using synthetic data want to make inferences about like the sample that you had at hand, then you want to be as close as possible, or do you want to make inferences about like the population, like that would be somewhere here that actually generated the sample at hand? And then you would want more variance to account, like especially to account for like the synthesization uncertainty as well. From what sample sizes onwards could this work well? That's the next question in the chat. So here in that example, without privacy, that's like 25,000 examples, and that works pretty well. So that's not too big. And in the example that we coded for like this even simpler shape, like this parabola, it was only 1,000 examples. So like those GANs work also pretty well with like smaller samples, but of course, like the more examples it actually sees from the distribution that you care about, like the better it gets. And like if it's high dimensional distributions like images, you would need more, like more than 1,000. Otherwise, this might not learn anything useful. So the celeb A with like, I guess 40,000 images is like a good size there. But of course, it's harder to collect and curate such large data sets of images. Just go back to training again. That's always the most fun part of like if we go make this a bit smaller, that it actually gets closer to those 64 by 64 pixels. They're not too bad, like I would say. Look a bit like paintings, maybe. But that's always the fun part, like to be honest, of training generative adversarial networks, to wait and see if it works. And often it doesn't, and then it's also annoying, but sometimes it's as exciting as waiting for the next like episode of your favorite series on TV. All right, if there are no further questions, I don't want to keep anyone around here and wait until something exciting happens. So like, thank you very much for your attention and the excellent questions. And it was a lot of fun. And I hope it was a lot of fun for you too. And I guess I will just hang around in the Zoom room for like a couple of minutes if any questions pop up. But on the GitHub page for this course, you will also find my email address if anything comes up. I'd be happy to read from you and stay in touch if you have cool ideas what to do with GANs. I would be very interested to hear about them. So thank you, and like have a great Wednesday and a great like last couple of days after summer school.
There is one more question in the chat. Would it make sense to pre-process the pictures? For example, align the faces and remove the background and train models for the background setting?
Yes, and like we kind of did that with the celeb A data set as well, right? We cropped them to the center, so like in a way to hope that we get the faces. Because of course, like the more similar the training images, the easier for the GAN to learn. Like if you have like a very diverse set of images, like let's say, I don't know, landscape, animals, cars, and faces, this would be very hard, like for the GAN to learn anything, right? So the more similar, the better. So I guess pre-processing the images is also one of the secrets, like from those high definition GAN pictures that is not often talked about that much. Because of course, it's because the networks are so cool and not like the manual labor that has to go into it before it.
Awesome. Thank you so much, Marcel. I don't see any more questions. There's a lot of thanks and yeah, thank you. Oh, there is one more question from Sven. When inputting missing values, should you thus use specialized GANs for each variable or a more general one for the combination of variables?
Again, like I don't have a definitive answer for that. Like the way I would think about it, and like how I would think about how GANs in the context of imputation would make sense is to try to draw from the underlying joint distribution. So in the best case, you would try to learn like the joint model for the data, and like this can also entail making specialized choices for variables. Like think of like those mixed data types. Like if you have like real valued data and categorical valued data, like you would need to make sure in the architecture that like you get the output that you expect for each variable. But I wouldn't use like a GAN for every variable separately. So I would try to learn like a joint model that tries to learn like the underlying distribution. Like that's how it makes sense. Otherwise, you could use like the chained equation approach with like, I don't know, flexible neural networks as well, which would probably also yield very good results.
Yes, Swen says thank you. And
yeah, that's
a lot of other things.
Great questions. Thank you all again as well.
Thank you, Marcel. Thank you. Good luck, everyone, and we'll see you tomorrow for the continuation of advanced courses.